start? Okay. I need to turn off this one first to give you an idea of what we are going to do today. Okay, so here is week number 8. Today we are going to learn something called LFT, okay, linear fractional transform. So the question is, why we need to learn about this? I never heard about this. Why I need to learn? Okay, so that's a question we need to ask. Why? So instead of talking about what, let's talk about why. Okay, and why. So as I told you that what we are doing here is to talk about uncertainty, let's say quantification or modeling. Okay, and in here we have two types of uncertainty. One is called structured and unstructured. Okay? Unstructured. From this side, we already learned in chapter 7 that we talked about the small gain theorem, robust performance, robust stability versus nominal performance and nominal stability, and based on what do we call small gain theorem. Okay, so that's what we learned last week. Okay, last week. So, but the main issue is we assume we know nothing about the uncertainty. Okay, but abound. Okay, but abound. We didn't assume any structural information in there, and in the structured case, we are going to deal actually in chapter, next chapter, okay? Actually, this is chapter 8, okay? Chapter 9, this is chapter 10. So in chapter 10, we are going to discuss about how to make use of the structured information, how to define what I call structured singular values, so that we have a detailed description of uncertainties. But how we can do that, okay? How we can do that. The main reason is we need a systematic mathematic, what I call vehicle, okay? Mathematical vehicle. So this LFT is a mathematical vehicle to help us to get ready to talk about structured singular values. Okay, singular values. So what is a linear fractional transformation? Say for example you have x, you have ax plus b. Okay, so if you have y equals ax plus b, then it's kind of a linear relationship, right? But what if you say, oh, I have y equals ax plus b divided by cx plus d, so then we define this is, you map x to y, right? This is called a linear fraction. This is a linear fraction. This is a linear fraction, the transformation. You instead of talking x, you use, so this is something familiar to some of you regarding testing transform, right? So it's bilinear, right? So this is more general, is in terms of more general in terms of called linear transformation, But if I suddenly tell you this one is still like we cannot link from here to here is like very vague that we don't know how this is connected. Okay? We don't know that yet. Okay? So what we really need to know is the idea of pulling out of deltas, pulling out of deltas. So I have uncertainties in the system. I want to pull out those uncertainties and draw a line between certainty versus uncertainty. So that kind of concept is called MW description. So you have uncertainties here, and then you have M in here. So then you have, and then you have W, you have Z. And W and Z. So. And this is kind of a MIMO case. You just think about partition M11, M12, M21, M22, sorry, M12. So this is a partition, okay? So basically, this is corresponding to known, this is corresponding to unknown, okay? Then you do this partition, so this is going to be detailized in our discussion, today. So with that, I hope you understand, LFT is some sort of mathematical mechanism introduced systematically to help you to do this type of separation. Okay? There are a lot of interesting properties, and there is also existing MATLAB tools to help you to do this job. And we are going to run examples for that. So if you understand why we need to study this, then it will be easy for you to understand what is this. So this is the outline of this chapter. Today, if we go faster, we probably can finish all of them. And we are going to finish right at 11 o'clock, okay? Because of my meeting of the 15, so I sent a reminder to everyone. So I'm going to finish at 11 today. So what's the definition? We answer why. But we answer what. But I think I explained to you why we started this. This is a mathematical vehicle. It is new. It is believed useful for studying robust control. So that's why this part is separated to the next chapter about structure singular values. Okay? So the key point is we want to make use of the known structural information about uncertainties such that our handling of uncertainty will be less conservative. So all the purpose here is to use structural information to reduce that potential conservatism. Okay? So let's move on to study this LFT, LFT tool. Okay? LFT tool. So basically we're talking about you have a system, you want to separate M and delta. Okay, delta. So there's two types of LFT. One is called upper, when the uncertainty is put on upper. And you also can do this way, so put it lower. So they can be interchangeable. There are some. So this is called lower linear fractional transformation, lower LFT for the M over delta. Okay, F delta. So this is F is a transformation. Okay, M and delta, M and delta. So delta has a suitable dimensions, and this is invertible. The reason we want this one to be invertible is to make the whole connection. Remember, we have a MIMO connection, feedback structure, there will be a serious problem of what? Well-posedness, as well as internal stability problem. So there is an internal stability, but if you have this inversion exists, so then you will be able to write it this way. So what does that mean? So basically you have M11, okay, and we say this M11 is perturbed by the delta, okay, perturbed by this delta. The delta is the uncertainty, and this is a MIMO situation. We have examples later on this. So basically I have a W1, U1, so W1, U1. So remember, what's the W? W is the signal. I use it to generate an output signal such that I use the transfer function between W and Z to make an assessment of my performance, okay? Sometimes you may say, oh, W1 is the same as U1. Yes, that could be a special case. But in reality, to more generally separate this, okay? So you can connect these two, okay? And you can connect this one as a Z, okay? But that doesn't matter, okay? We should get used to this. So this is for input to change the system behavior. U is the input, Y is the output that you measure. So this is uncertainty. So this is a reference for performance assessment. This is inner signals that to form this type of interconnection of your uncertainties like this. Okay, so this is called W. Delta M delta structure. This is called lower LFT. So if you write in the matrix format, so you have W1, U1, Z1, Y1, so you have different dimensions here. Then you do partition to the M by this way. So what you really care is from W1 to Z1. That's I care the performance. But inevitably, it will be influenced by the delta, Okay? So the Z1 will be like M11, W1, M12, U1. Okay? I want to remove the U1, so I need to inverse. So U1 is delta Y. So then in the end, I write M11, W1 is this one, and plus another term. So FLMW, M delta. So this is called lower format. And this is again upper LFT. If we don't say anything, we say this is lower. You can see if it's upper, we put the U here, upper. Okay. It's similar. You do a partition here, okay? You do a partition here. You have something similar. But if it's, oh, I want to derive this one. Yes, you can. It's by simple algebra, according to the author. You should be able to get this one right, okay? You should be able to do that. So, because of the invertibility, guaranteed invertibility, we say that this M delta lower LFT is well posed. And so that is the matrix format. So we assume here, this is a technical assumption, like C is invertible. Because you need to invert the C to make this thing happen. Okay? So here is something, remind you ABCD, right? ABCD. But this is a scalar form, this is a matrix form. Okay, matrix form. In other words, anything you can write in this format, okay, in this format, can be written in MQ format. So you can pull out the Q from this So X, you can pull out the X is like Q, and A, B, C, D are none. So then you can form as if you write the M delta format. So treat the Q as delta. So this is a linear fraction, okay? Then there is a variable in the linear fraction you can pull out, and forming, this is A, B, C, D are none, so M is none, and the Q is unknown. So that is a beautiful connection here, beautiful connection here. So it's a law LFT, okay? Then you construct M. So basically we answer this question, okay? Answer this question. So if this X is treated as uncertainty, okay? All others are known, this is unknown. How I can write X out of this and put an M in here? So I can draw a line between unknown and unknown. Okay. How I can do that? So it is very interesting, and this can be generalized into matrix format. Okay, matrix format. So the idea is simply FL M X. So they use the Q, and they have a matrix form. But doesn't matter. So if you know how to extract this, then you basically can handle everything else. Okay, that's the idea. That's the idea. So we're going to see how this is very useful to help us to separate unknown, uncertain versus nominal. So this is nominal, this is uncertain, unknown. Okay. Don't get bothered by all these derivations. You need to understand the motivation behind this. So then they can do upper, so this one. So if you have this inversion in the left multiplication, in this side, you can write the M matrix in this format. So because this is different, it's a matrix format, the dimension might be different as well. So you can write two forms, okay? So these equations, you don't have to memorize it. But when you need to use it, just check this in the textbook. So you can, in the matrix form, can separate the knowns and unknowns, okay? So again, the reason we do this one is because we made use of a structure in here, so linear refraction structure. And you will see in many of the control problems, okay, the uncertainties and the nominal systems are intertwined like this format, okay? So this chapter is mainly talking about how to systematically separate unknowns, uncertain, and certain parts of the system model, okay? And so, M12 is invertible, so this is what M12. So this MQ, using this M, this format is this one, this is A plus BQ, okay? So that is this side. So upper and lower, okay, upper and lower. And M21 is invertible, you can write another format like this, okay? Depending on the invertibility condition, okay? So these are just the partition matrix operations. You may feel this is not very straightforward. Let's see an example, okay? So this example, if you treat W1, W2 as identity matrix, so it's a standard closed loop system. You have an output, noise, disturbance in front of plant, control signal. This is this is also a filter, okay? A feedback controller. This is feedback controller. This is a feedback filter. A feedback filter, okay? So now let's say this is a MIMO case. Everything here is a vector, okay? And you have filtering, weighting filters here. So instead of directly use this output here, I filter it so I can put emphasis about which frequency I care. So you formulate the V. So then I also have control energy. I want to say how much control I put it in. So it's a filtered control signal. So I use this signal and this signal as signals for performance assessment. So by doing that, what we have here is a nominal system with W in and Z out. What are the in? In is D and N. In is D and N. You write W there. So it's 2 by 2. And what is V? What is the Z? Z is performance. So I use this signal and that signal as my performance measure. Okay. And so in the end, I want to check from W to Z whether my closed loop transfer function will be satisfying our performance specification. So in this case, I pull out what? I pull out my K. Pull out my K because this is known, this is known, this is known, this is known. K is also known. I pull out the K. Okay, I pull out K. So I want to understand how I can write this LFT case so that I know the whole system with this K explicitly pull out to study for different Ks what is my TZW, transform from Z from W to Z. Okay, W to Z. So by doing that, we can write a 2 by 2 matrix. So what I say is, basically you should say G equals WU and ZY. Okay? WU and ZY. Let's do this. Let's do this. I think it's a good idea we walk through this. Okay? So this is an example we should feel very comfortable in the future, okay, in the future. So basically my G, okay, G, it has two inputs. One is W, one is Z, okay. So what I care is my TZW. So from W to Z is my TZW J omega, okay, we can write it this way. Okay, this is a transfer function metric. It's a closed loop transfer function matrix. So then this signal, what they put here is U and Y. U is here and Y is here. It's an actual control signal and actual measured signal for feedback. Okay, so. So I pull out the K. Then I can discuss my stability. So according to small gain theorem, so I know what is the robust, whether the K is considered as a robust stabilizing. It's making the overall system stable. Giving K, I can check that. Okay, it's easy. So it is interesting to see that we are going to write Y. Let me put Z in the front, in the up. So Z divided Z and Y. It will be, what's this one here? You have W, you have U, right? You have U. Okay, you have U. So you know that Y, I didn't do anything here. So Y and U, Z has 2, Y probably is 1. Okay, maybe it's a vector, but it doesn't matter anymore. So what I put it here, you can see Z is W. Remember, W is dn, okay? And Z is V and UF, okay? V and UF, okay? But remember, UF is nothing but W ZP, okay? W2P, okay? W2P. So W2 is the V, okay? So let's do this. So U times, so this is W2P 0, 0, 0, okay? The reason is I have the dn, okay? I can write this like a dn, okay? Like d and n, okay? Yeah. So d times W2P, okay? W2P, okay? You have something, D will, like D, P, W2 to V, right? So this is like, here we have V and UF. So they're like V equals D, P, W2, okay? Will be, so this one should be W2P as well, okay, with N, okay, with the N. Okay. So then you have a W1 in here, and minus F, and there's, sorry, this is minus F, there's minus FP, there's minus FP. So from the signal flow, say for example, Y equals what? Y equals F times N, okay? F times N is like this. The minus sign is here because of that. So then you have a FPD, you should say DPF, okay? DPF, you should say that way. So this is DPF, okay? And you also have another one, the Y here is because of Y equals this one and this one, so you have a UPF, okay? You have also U signal here, P and F. So then I think the last equation here is clear. You simply write Y because of okay, let's say Y because of three things. One is D, one is N, one is U, okay? One is U, okay? The Y because of three things, U, D, and N, okay? U, D, and N. So for the D, we know that D will go to D, P, and F. So in MIMO case, you should write D, P, and F, okay? And you have a minus sign here, okay? After F, there's a minus sign. So then you add, okay? N will go to F, minus sign, so it's minus F. So you should put a minus F in here. That's why it's this term. And U, okay, so you have U. This signal, don't forget, you have signal U, P, F, minus. So here you have minus FP, U, P, F. So this is a MIMO. In the MIMO case, you should also have this habit to have a signal go from right to left. You follow the signal flow, but you write from right to left, so you don't make mistake. So we explain this one. Similarly, we can do this. So let's say, what's the V? V is W2PD, and you have W2PU, and others are 0. Okay, so let's say, what is the V? V will be signal due to D to V, right? Also because of U to V, right? So only two. There's not anything else, okay? Okay. So that's why we have a W2P. So you have a going to P, then W2, then P, then W2. So you have the V, okay? So then for the UF, then that is only one, is a W1 and U. So the UF is the U times W1, okay? So with that, we explain how to write this G. And don't get very confused about, so these are transfer function matrices, okay? By drawing this line it's just partition. It is not the one we used before, saying that G is A, B, C, D. If I draw the solid line in separation, this is called what? A realization, okay? A realization in state space. But here we are using what? Dashed line, okay? It's different, huh? So for this simple MIMO feedback control in the classic sense, we say that there are control variables we care, output variables we can measure, and also we have reference input W, and Z as output used for performance assessment. Of course, you can use Y for assessment, but to be more general, we use Z. For example, in our case, we use Z as V and UF. Both are filtered signal to say that you can add in you as designer preferences. Okay, you have your preferences. You can say, oh, I want to have this frequency range more highlighted, so that you can use high frequency or low frequency or band pass filter and so on and so forth. So the filters are very important. Okay, very important. So in this case, you can see that we show steps to put this LFT format. So the G is the transfer function matrix between this. We totally without a control signal in here. Oh, sorry, control. We don't have this guy in here at all. Okay. No, so there's a separation. There's a separation. Okay, makes very good sense. So this is a hint how you really write this format. I did a signal flow there for you, but in reality, there's a way you can say you remove the K first, then start to study from where to where. Okay, because otherwise you might be confused and say, oh, from N to V, of course you have a way to do. Okay, no, you don't, because you don't get to here. Okay. So for each of these 4 blocks, you can see you have a W2, P, F, W1. So these are transfer function matrices. So they are different dimensions. Okay. So for each of them, we can consider to make what we said state space realization. Okay. State space realization. So that's what do we have? So you can write this format and do realization about the G. There's a simpler way without doing this. You can do directly realization of each individual transfer function matrix here to do state space realization. we are going to use the subscript like A, P, F. These are filters, okay? Feedback filters. W1, W2. W2 is mainly due to the V, and W1 is mainly due to the control signal. W1 is for control filtering, W2 is for output filtering, okay? So the V is for output, U is for input. So that's why we have this W2 is output, W1 is input, the filter, okay? Again, the filter is for putting your designer's personal preferences there. And you can start to write all this type of state space, and we always assume that the D here is 0, which is reasonable. It's a physical system, you don't usually have that. However, when you put a filter, it's possible you can have DU, DV. That's you artificially put there to manipulate the signal. It could be what I call relative degree 0 in a size of case. And not strictly proper, so then this can be non-zero. And this is possible, okay? So therefore, you can see that we can write state space vector, xp, xf, xw, so stack this together. So we have, this is x dot, so this is a x, this is a state equation, and this is what? So this is called performance assessment output. This is the system real output, measured for feedback, okay? Of course, you choose everything here the same, then y is the same as z, but we separate these. So that's why in robust control, we have state equation, we have output equation, and we have we call Z, I invented it, I call this is output for performance assessment, okay? I use this is Z for my performance assessment. I only care about closed loop transfer function from my W to Z. I don't care anything else. So performance-wise, I only care about T, Z, W, the closed loop transfer function between W to Z.
But it means that Y should be stable if we ensure that the transfer function between Y and Z is working properly?
For stability, so this related interconnection, I think the stability is related to this A matrix, okay, related to this A matrix. And the stability, of course, is influenced by the feedback in here, okay? So we haven't discussed introducing how to design a U yet. U is the only thing that you can change, okay? U equals something called state feedback or output feedback or dynamic feedback. That's yet to be designed. We don't discuss this one yet. But by writing this this format, okay, by writing this separation format, giving a K is very easy to use Smolin theorem to tell whether the system is stable or not. It's much easier to check. Okay?
Okay.
So this is the separation part. So we are still talking here about the P matrix here. This big matrix is called P matrix, G matrix, okay, G matrix. And how the G matrix can be interpreted like a state equation, output equation, and the output for performance assessment. So the A, B, C, D are written in such a way. So that's why in robust control, usually in control you have this one and this one. But now we added this one to be more general. So I think you get a feeling of this separation idea, okay? So here we use an example of separation of controller and the plant, as well as in state space, okay? State space. So now we are getting to the fun place, okay? The fun place. So please pay attention. This one is called after putting out the delta and the case. So we need to have a separation. We know how to do the separation of the controller, right? We just show you an example. But what if I also have uncertainties? I want to pull out these things out. So I have already pulled out my controller, like previous slide. Now you have some uncertainty, delta 1, delta 2 inside, delta 3 in there. I also want to pull out, okay? I also pull out. So this is something we want. And this is what? W, this is Z. So D is for performance assessment. So then this is for feedback and control. And this is the internal connection of those uncertainties. I pull out the uncertainties. So once I can pull out, what do you see? This delta becomes what? Diagonal, isn't it? Diagonal. So that's why is the big delta matrix may not be fully populated. It's simply diagonal. Then I can sharpen the uncertainty bound much more precisely, and the design of bus control is much less conservative. So that's the whole purpose of this separation of unknowns and knowns, and hopefully we can, while you separate these, you can get the structure out of it. And in the later part, I hope that sometimes when you pull out the delta, it could be block diagonal, okay, block diagonal. Okay, you can pull out all of them, you just block diagonal, like for each block might be fully populated, okay? Okay, but I have a different sub-blocks. So this could be scalar or a matrix. And inside here, we assume this is unstructured anymore. Unstructured, not this structure, I assumed. So because you don't have a way to separate these. So while you pull out this one, you are already using what I call prior knowledge about the plants, physical parameters, and so on and so forth. Okay, so I'm hoping that the whole system made for inner system like that. So from user point of view, user basically say that how this system is doing. I gave a W and checked the Z. So that's what they really care, okay? What they really care. So with that, I hope you guys feel the meaning of separation, okay? Separate the K, separate the delta, having a structure information here, and the benefits I'm going to show you after introduce the structure singular values. It will make a lot of sense. But at this point, we are going to run an example, then we finish. So I hope that you are going to see the LFT and upper or lower start to make sense. Okay, start to make sense. Let's see an example here. Okay, so I have. From W to Z, I have a system, but there are some parameters connected. So from W to Z, I didn't talk about transfer function metrics. Okay, let's try to make things easier. I have certainty A, B, C, D, and E. They are all precisely known, but those deltas are not known. Okay, they are uncertain. So then we do some simple manipulation. We find out Z and W, they have this relationship. And I want you to help us to separate the knowns and unknowns. What do you really do? What do you really do? So basically you have block diagonal here. You have two uncertainties. Delta 1 showed up here, delta 1 showed up here, delta 2 showed up here, delta 2 showed up here, right? Okay? So the delta shows in this way, the 4 places, right? 4 places. Then you start to define what you should do. You define what is in, what is out. Okay? So outside is W to Z, but what's inside? Okay, what's inside? So what we really need to care is the Y and the U. Y and the U is basically we are using for the description of this is uncertainty, then U is here, Y is here. So we define around the deltas, We define this is first uncertainty, this is the second uncertainty, this is third uncertainty, this is fourth uncertainty. So we define what is Y1, U1, Y2, U2, you know, we define that, okay? Mm-hmm.
U1 and Y1 are they? I mean, it seems that Y1 is the input instead of output, right?
According to the convention we used in here,
Yeah, I see.
U is out. U is out of the uncertainty. Y is into the uncertainty. Okay? So then U is into the nominal system. So that's why the delta, this is tricky, thank you for spotting that. So it's it's kind of unnatural, okay? Okay, it's unnatural. So U is, okay, U is out of this uncertainty. Y is into the uncertainty. And the output is from the nominal system. Getting into the uncertainty, come to the U. Okay. So I hope this is not very surprised. Okay. So then you define this pair. I write U1, U2, U3 as my input to M, and W also is part of that. So then once you define that, it will be getting very straightforward. You put M in here. So Y1 equals what kind of Y1? Y1 is here equals what? Okay, equals this guy, this guy. Okay, so this guy is 1. You have here, you have U2 minus E, U2 minus E, U3 minus D, so that's all. Okay, so that's why you have this. So you can do something similar, and you have this structure. This is a partition matrix, M11 and 22. So then you can separate that. So what is the TZW? So from W to Z, what's the transfer function? It will be upper and W. Okay, because this is a lower here. Okay, so then this delta is you have 2. So you have partition of 2, so 2 sources, but each one has a repetition here. So as I said, so this is called structured uncertainty. I already pull out the structure. Did I? Yeah, so we separate the knowns. So this is a nominal system, M. So everything inside here are precisely known. And then once I do MW, it turns out that the TZW, so this one is called what? This guy is called closed loop transfer function from W to Z. So in LFT language, closed loop transfer function is simple LFT. upper LFT of M delta. And then, okay. But you may say, oh, can I write in lower? Yes, it's possible. It's just a matter of your preferences. You want to upper or lower. However, by the convention, it's a convention, okay? So we usually leave the upper to delta. We leave the lower to K. So you have a nominal system, controller, uncertainty, okay? So I hope at this point, this picture makes very good sense. And again, you feel there is a systematic way to pull out K and pull out delta at this point. Just follow this principle. You can make these two separations without getting very confused, okay? Because we're talking about MIMO. And we also want to leverage the structures inside here. Okay? Therefore, this LFT framework is absolutely useful. So, one of the ideas you pull out the delta is idea of once you want to pull out, you just remove them. Then you start to write this M from W to Z, okay? And you define the input and output, Y1, U1, okay? As the uncertainties, okay? So then you will have delta, put it here, put it here. So again, this is the same, okay? This is the same. So that is, that's an example. So this is a static system. We didn't add transfer function here. Next example is going to show you an example like this. So you have a mass spring damper system. Okay, you have mass spring damper system. And it is very natural that you assume that you have a nominal M. You have a M tilde is the nominal value. And C is also nominal value. K is nominal value. And you have delta M, delta C, delta K are uncertainties. Okay, uncertainties. Okay. So how I can pull out these deltas, okay? And still I write my M such that my state space representation here will give me the output, okay, so x dot, x2 dot in that format, okay? So the reason we do this one is that we have double integrator in here. So the force plus this, so you have three terms, okay, three terms. We'll add, so this is this mass, then the x double dot. So that is the whole realization. In this thing, you have uncertainties embedded in the system. How you pull out this? The idea is similar. Okay, the idea is very similar. Okay, so you can do M and delta, M and delta. There's another high maneuverability aircraft example, similar to the previous one. You have some parametric uncertainties in there. Then you also can get this, what they call interconnection matrix nominal system here. That example is given in our textbook in detail. We are going to continue to talk this Thursday We have a Simulink block diagram written in terms of the aircraft.m. We are going to have a project around this one, okay? For this aircraft simulation, okay? So it is actually a benchmark system, right? Benchmark system. So we'll stop at here, and I hope, let me summarize what we did today. Today we introduced the LFT, linear fractional transformation as a mathematical vehicle to help us to pull out unknowns or pull out controllers. So we have a nominal system G, okay, then we have controller and uncertainty. So that delta uncertainty will automatically have some sort of structure information, say for example, diagonal or block diagonal, okay? So all those things are useful in practice, and we have seen some examples. And the next lecture we are going to see more examples. Then we are going to dive into next stage, how we can leverage this structure information in delta to have a much less conservative design by using the newly defined structure singular value SSVs. Then we are going to talk about the SSV, how to guide us to design the K. Okay, so step by step things are getting more and more interesting. All right, so let's stop here and see you this Wednesday. Okay. All right, thanks.